I'm the project manager of distributed spacecraft autonomy at NASA's Ames Research Center. That's in the Intelligent Systems Division. We do a ton of software. So this kind of makes sense that this is what I come to talk about. Before being a project manager and giving everybody a bunch of problems, I used to write flight software as my day job. Generally, what is command and data handling? That's what CDH stands for. And these blocks here are things that I'm going to cover during this talk. So if I don't hit it by the end of a section that's coming up, I probably will hit it soon. In general, what you're trying to do is you're asking the question, like, imagine you're some of the first spacecraft operators. This is the Explorer 1 down here on the bottom left. That's Vanguard 1 over there on the right-hand side. These are the first two spacecraft launched by the United States. And Vanguard over there to the right, you can see to scale, those are some of the engineers integrating it onto the rocket. It's a nanosatellite. And the fundamental architecture hasn't changed that much when we're talking about nanosatellites. You should put yourself in their shoes and think about, how do you talk to it? How does it talk to you? What are you saying to one another? And how can you tell what it's actually doing in response to what you're saying? So how they did it then was essentially direct control via radio transmission. We still do this with radio transmission. There was no computer on board these old nano spacecraft. A computer was actually a bunch of people in a room, mostly women, doing math. That's what it was at the time. In these cases, the spacecraft was always listening and beaconing. And you essentially had 4 components on the spacecraft. How we do it now is almost the same thing, like I said before. This is EDSN, or NODES. It's a mission that was run out of Ames. It unfortunately achieved very low Earth orbit and went into the water. And so the follow-up concept was only 2, but the original concept had 8. And these are about the same size as Vanguard 1, which is what's so cool. And they have very similar components. And there's a link to the paper there. Right? But 2 new things were added to the basic components of EDSN that make a modern CubeSat. That's the computer and the GPS antenna. And essentially, every single CubeSat you make will have these components minimum. And your CDH is the glue between all these components. It's the way that these components talk to each other, and it's the way that you talk to these components when it's up there in space. And in general, when we begin to talk about the new stuff, we begin to think about processors and how we select our processors that are on board our spacecraft. So there's a few decisions that you have to make when you're doing that. One of them is, do you run on bare metal or do you have an operating system? Bare metal means that you're directly flashing the device and you're writing code that's running on the device itself. An operating system is more flexible, but requires more compute. You'll also have to think about your power budget. Can you afford to have certain components on the spacecraft itself? Can you generate enough power, and can you dissipate the heat from that generation? You'll need memory, both RAM and non-volatile, and you'll want to have interfaces within the spacecraft for these components to talk to one another. And lastly, you'll have a data budget. So as you're generating data on board, where is it stored? Do you have enough memory for it? Things like that. All right, I wanted to talk a little bit more about some of the hardware approaches, the computers you can have on board. Nowadays, they run from single board computers, which are really cool. These are like BeagleBones, Raspberry Pis, NVIDIA Jetsons, for example, different small board computers. Your Apple makes single board computers too. It's called the M1 chip, the M series chips. It's the A series chips that are in your phone. These are essentially single board computers within your smartphone. And then you have microcontrollers. So these are like, you can think of the Arduino, for example, is a microcontroller. This is an overview of kind of how you would think about your operating system selection. I mentioned before that there's bare metal. I really recommend doing something like Linux on board if you're going to do an operating system at all. In the past, VxWorks was very popular, but essentially everybody's moved away from that, as far as I can tell, for new missions. And then you have the option of a real-time operating system, an RTOS. There are many RTOSs available that you can kind of fork and customize yourself. I'll not go through the details of this right now. In general, you do have to worry about radiation. In LEO, you have to worry about it much less than if you're leaving LEO, low Earth orbit. But there are solutions to the radiation issues that you'll face. Generally, higher inclination orbits experience more radiation. And there are particular memory solutions like hardware that you can purchase in the way that it's designed that can mitigate the effects of this radiation. Radiation tolerance and radiation hardening are, in some sense, buzzwords. You have to really look at the effects of the total ionizing dose and so on the components, and look at the actual way that the memory is built to assess for yourself and for your own team how reliable you think it's going to be in a particular radiation environment. And you should do all the work you can to understand your radiation environment. You may have requirements that come out of this in terms of like what orbits you can support. In terms of mitigation strategies, shielding is always great. Just add more aluminum. It works pretty well most of the time, especially in low Earth orbit. But you also want to do things with CDH, like error correction encoding. There are some pretty common approaches with ECC that vendors already implement. And when you're looking for memory and you're looking for processors, you want to look for components that implement error correction coding schemes, ECCs, already. You'll be able to find that in the ICD and the spec sheet. As you're going through that, you'll notice the different approaches, but in general, you want to find something with error correction coding. It's possible to implement this yourself, and it is actually recommended to implement some additional things yourself, depending on what part of the mission you're doing and building on your own and what part you're kind of buying and contracting out. MD5 is a very common hashing scheme that allows you to quickly calculate by just looking at the front bits or the ending bits of something, whether a change has happened in the file. So where you would want to do this, for example, is something like your operating system or your bootloader. If you're looking at this part of your software that really shouldn't change over time, you want to start up every time, don't you? You look at the MD5 hash, the MD5 sum, and you can tell if that's changed. And it would change because there's been a radiation event and you've had a bit flip or something like that. TMR is triple modular redundancy. So the idea here is if you have 3 of something, a radiation event is unlikely to change all 3 things at the same time. So by comparing your memory locations or comparing these 3 things, you can find 2 that are the same and the one that was different. And then you can physically correct the one that was different and get everything back to a stable state. So that's TMR, also a very common scheme that I recommend. Another way to deal with and mitigate radiation is to use memory partitions. So what I was talking about before is purely software. This is also software, but on your silicon, on your chips and everything, you have different memory banks in the physical areas of the chip. And so when you make partitions, you're telling the computer to block off this little area, essentially, and then block off this little area. This is another strategy where you may want to do TMR between different partitions, for example, before you boot into your operating system. What's nice about this is, like I said, it's in different physical locations on the chip. So you're unlikely to have a single event upset or latch up or something in 2 particular places in the exact same part of memory at the exact same time. So you can correct it. And again, going through the file system, there are trade-offs to using particular types of file systems, and I won't get into too many details here, but essentially, if you're caught writing to something and you get a power off and you're already allocating a memory and then you get power off, depending on what file system you're using, that can cause that area of memory to be permanently unreadable. And so really what you want to do is think hard about your file system and when read and writes occur and how often you're doing that, and chunk that up into smaller or larger segments, depending on what your strategy is here. All right, so let's talk about starting up your system. So when you start your spacecraft, you're generally going through this process listed here, where you have your bootloader, you load your kernel, you load your operating system, and then you load your flight software. I already talked about TMR. Our group has implemented TMR at the bootloader level before. We'd have a few different partitions of our operating system, what would be on all these different partitions. So we would basically have the same operating system, flight software, and kernel all on 3 of these partitions. And the bootloader itself does a MD5 hashed based TMR. So right, we're looking at to see if there's been a change in any of these 3. And if there was, we're going to choose a good one, and then we're going to notify the ground, essentially with some telemetry. You can choose to try to correct that on board, but we prefer to do it on the ground and then upload and reflash the partition ourselves. You can do MD5 and TMR at any layer here. You can even have redundant bootloaders. That's not something we did, but you can do that. And there are additional stages to think about with startup. So you've got your hardware stages. A lot of what I'm talking about here is going to be software focused, but I'll still touch on some hardware solutions because at this low level, they are very intertwined. You can do memory checkouts with your chips. Some chips will even have ways to do this, like I said, with error correction coding that you can kind of read directly and correct it over time. You want to have different software checkout stages as you start up. So again, I mentioned TMR, reinstalling, failover. The hash checks is another way to say MD5 essentially. There's a lot of different approaches there. And then eventually you reach a monitoring stage where things are running and you want to try to detect if you get to a part of memory where you've had some event that's occurred. You've had something flip. So serial protocols. This is when you're talking over your PCB, your printed circuit board. Each one of your components are going to be on this PCB. And you also want to talk to your other subsystems. This is all part of CDH. If you remember, I was saying the CDH is really the glue that's holding all of this together. There are advantages and disadvantages to using different approaches like asynchronous signals essentially to communicate and synchronous and so on, and also differential signals and single-ended signals. So something to consider if you're using one single line across your PCB, so that's like one cord to communicate, is that the more communication you try to put on that, the harder it can be to read it at both ends. So there's a few different approaches you can take. You can take a multiplexing approach, which basically says you're only going to send one thing at a time, and you're going to clock that. So each component's going to send something like at a particular time period. That's where something like a real-time operating system becomes really beneficial, right? If you're trying to mux this. You can also separate the comms buses entirely. So instead of using one cord, you can use two cords, basically two lines in your PCB. And you can add a buffer, right? So if information's coming down the line, instead of trying to read it all as it's coming in, you can have it stored, and then you can slowly read off of that buffer instead. All of this helps if you're really worried about errors across the line, because radiation can not just affect your memory locations, it can affect the actual signal that's going through your PCB. So you want to think about that too. And you also want to think about situations where you get a bus lockup, where that line stops functioning. If you're not able to communicate to other things on your board, what do you do? One of the things you can do is you can use a watchdog. This is essentially a dedicated set of lines or software loops that are constantly checking for liveliness and trying to detect if a component is locked up or not functioning. Watchdogs are a really core component in flight software and PCB design and hardware design when you're making your CDH. It's something you would do with both your hardware and software team. And you two really want to be talking to one another as you're doing that. Here's an example of a simple CDH watchdog. So you may have a power supervisor that just makes sure that the CDH is powered. If this goes down, you may want to try to automatically reboot your CDH, which in this case, you can imagine that's your primary flight computer. And you can say that the supervisor, if it gets locked up, would reboot it after 30 seconds. That's one example. Now, if you added a microcontroller to this, let's say you have some camera that's run by a microcontroller, you can have a few different watchdog designs. One is, let's say that the microcontroller can fail into itself. So if there's some register that it's reading from, it's trying to read memory from this guy, let's say this is where your image is stored, and it detects an issue there, it can soft reset itself to try to read that again. Another thing it can do is the same situation as the primary flight computer. You can have it reading from the power line through a GPIO pin. And if it latches up or you're not getting the correct data you expect from it, you can soft reboot it in like 30 seconds. Another example is to have your CDH control the microcontroller itself. So you may have a set of states that you're monitoring on your CDH. And if you reach a weird state, you can go ahead and put it back into a new state or power reset it. And then the other option is to have the microcontroller itself talk to the CDH and then basically ask for a power reset. All of these are valid ways, and you can even do all of these at the same time of approaching sort of mitigating risks with radiation and latch-up events and so on. So this was all hardware. You're going to have software controlling this, but this is essentially all hardware. You'd want to have dedicated lines for this. You'd want to have dedicated timers for this and so on. housekeeping and counters are essentially the bread and butter of telemetry. So when people talk about telemetry with spacecraft, in my opinion, they're mostly talking about this. This is the sort of stuff you'll look at when you're operating. And it's as simple as, let's say you have some software that's controlling your beacon. That's like spamming out a hello world thing so you can track your spacecraft. In this software control block, you may say, okay, when I receive a send housekeeping command, I'll increment by 1. If I get an error and I'm not able to just send this, I'll increment that by 1. If I get a rejected, you expect this could fail in some way that you've already thought about, you can call that a rejected. And then if it actually executes, you can say that the command executed, and then you can increment your beacon counter. What's nice about this is you can design the software control flow in such a way that your executed housekeeping, your error housekeeping, and your rejected housekeeping all sum up to be the received housekeeping. So you can back out a state from partial information with this if you need to. Just adding simple counters is great too. Anywhere in your flight software, you can add a counter to know that you've got to a particular line or that you've finished executing something. You should do that because this is very cheap to downlink. You can make these things like very small integers, and those are very easy to downlink in your housekeeping packets and your telemetry packets. It's much better than having a print statement that says something like, I got here. Like we all do that when we're coding, and that's fine when we're initially designing something. But at some point, you're going to have to downlink that data, and that string is much larger in terms of bytes than just a simple integer that you're incrementing. Here's an example of kind of what I was describing before up there on the top right. Inside an actual housekeeping packet, you would want to have something that's like your app ID or your software control ID. So let's say that you have some software architecture where you have a beacon application in it. Let's say the beacon application number is 01. That's the only bit of new information there. And then you want to have some time associated with your housekeeping as well. So here we're incrementing by 1 second. And in this example, we receive 2 more requests to send out a beacon. And it sends it once, but then it actually errors once. And you can see that incrementing there. Down there below is an actual in-flight diagram of housekeeping counters for our spacecraft that we are running on orbit right now. So we have 3 spacecraft that are doing cross-link communications to one another. And we want to know when they're receiving packets from one another. That's a very critical bit of information for us. In this particular diagram, the gray is areas we hadn't downlinked yet. We probably have a better version of this now that's completely full, but this is what I put for the talk. And I want you to notice that it doesn't always do what you'd think. And for those of you who aren't familiar with something called integer overflow, that's where in computer science you fill all your bits up and then it rolls back over to 0. That's what's happening with this sawtooth pattern here. It's very important to familiarize yourself with what these housekeeping counters look like over time, because that's going to give you an intuition of what your spacecraft should do on orbit and what like nominal operations looks like. For us, when 2 spacecraft are connected, we get this longer drawn out sawtooth because we're all talking to one another. When 3 spacecraft are connected, it like squeezes in. And so we can see just by looking at a glance, we don't have to do any fancy scripting. We can just see by looking at a glance how many spacecraft are connected to the network essentially. And you can even see moments where connection drops out, like around here, if you can see my mouse. You can see kind of where it levels out and then begins to spike again. So understanding your housekeeping packets and even choosing to design it in a way that's friendly for you and your team is incredibly important, because we like to imagine like flying the spacecraft ourselves, but really you're just looking at this stuff. And then that's what you have to use to decide what's going on orbit. So the sooner you can get used to looking at this, the better, instead of those print statements and so on. Synchronizing and managing time is very important. The importance of choosing a time standard between your spacecraft and your ground system is incredibly important. You want to be able to synchronize events on orbit with when you sent them, and you want to be able to plan for events on orbit later. I recommend choosing some standard system like Unix time or UTC or something like that to be your primary time on orbit. And you may even want to have, in some cases, a dedicated oscillator, which is just a clock. A lot of single board computers have dedicated clocks and so on. You'll be able to find information about how accurate these are over time by looking at ICDs and spec sheets and so on. If you have to have very like quick sub-second controls, you might need to look at a more expensive dedicated timing system. I would really recommend, especially for small sats, to stay away from that. Most single board computers will have a good enough oscillator for you to operate at like 1 second. You really want to consider things like leap seconds as well. A leap second might not sound like that much, but if you're trying to back out the location of your spacecraft and you're using a propagator to do that, and there's any delay between the two-line element, which is basically like an orbital element that you use, it's a bunch of math to track where your guy is. If you're even 1 second off from that and your TLE isn't really fresh, you could be looking in a completely wrong part of the sky to try to talk to your spacecraft. Thankfully, for the duration of our mission so far that we're currently running, there has been no new leap seconds, which has been great. But you should keep an eye on that if there's going to be leap seconds at all. This is just more information and synchronizing time. And you want to think about what happens to your time when you reboot. I'll make that point here as well. Because there are different what are called epochs, this is where you consider like time dates at 0. Sometimes when you reboot your spacecraft, in our case, it'll sometimes think it's the year 2000. Sometimes it thinks it's 1980 when it reboots, depending on the type of computer that you have on board. And so you've got to be really careful about that when you're designing your system. And potentially you would say, okay, if my single board computer, when it resets, it always thinks it's the year 2000. Maybe you just design your whole system to be indexed at that year 2000. So you don't run into any problems instead of choosing whatever the other systems have. And I do think going with what your single board computer's default is oftentimes the best, or what your main computer or microcontroller, whatever that default time is probably the best choice. This is the last bit here because I'll get into some more testing later, but a last note about hardware when you're designing your system is that you want to make sure you have access to all of these data lines. So I was talking about the different types of communications you can have between your components on your PCB. You really want to have access to directly reading those lines in case something's going wrong and you need to debug that during your integration and testing portion of your mission. That means that whatever boards you have to fly, you're probably going to have a breakout component you're not going to use in flight, but it's going to be really important for your design and testing portion. So that's what this is getting at. And the EGSE is the electrical ground support equipment, is what that means. The last point here is that while you should do long distance radio tests, you often cannot. So having a way to disconnect that and then send that over a different line to test your signal processing is also really good. So we get into firmware and software. I've talked a little bit about where the PCB hardware design overlaps with your CDH. And I would call that area of overlap firmware. The reason being, essentially, it doesn't change that often. So once you have designed your system, you will have a firmware flash to your system that's going to be handling your communications, your local communications on your board. You're also going to have firmware that's associated with things like drivers for particular components or things that are essentially not your flight software. It's still software, but it could also be written in something that's like assembly or a really low-level language, not even written in something like C or C++ or Python. It's just the really low-level basic communication stuff that you then build on top of. So your software would be using something potentially like Python libraries or the C standard library. Those libraries sometimes rely on firmware that is vendor specific, and that's another way to think about the distinction here. Software is also released frequently, and you're going to want to update your software on orbit potentially. You really don't want to update your firmware on orbit because you can risk bricking your spacecraft if you do that. Having a nice clean separation between the two when you begin your design is really good. This was sort of jargon, but my point here is that when designing the subsystems and components, it's very important to think about this, especially when interfacing with peripherals, using a combination of different types of compute. So you can think of like integrated circuits, microcontrollers, and your single board computers. You want to have some firmware that's kind of driving the communication between all those. You want to think about the frequency of updates. Another distinction is that if it needs a watchdog, it's probably firmware. If you're using housekeeping counters, it's probably software. As you're developing your software, you want to have a workflow. You do not want people to be sharing files via email or Slack or whatever and saying like, this is like flight software new_new. That's not good. You want to have some sort of definition of how things should occur, what the priorities are, and what tasks are being assigned in terms of developing the software. And you want to have meetups related to this at some frequency, and you want to have peer reviews of the software as well. So you want to actively go through and encourage your team to participate in this. And another thing you should do is something like continuous integration. I'll get into this a little bit more later. Actively documenting your code is very important as well. There are cool tools like Doxygen, where you can put a comment at the top of your function. And then when you are done writing your code, you can actually run another program that will auto-generate documentation for you and even auto-generate things like block diagrams and sequence flows. When we first design our flight software, it's cool to do all the diagrams. Like that makes sense for a big build planning. But at some point, when you generally know what your high level modes are and things like that, switching to using a Doxygen-based or automatic generation of your flow states and so on is really the way to do it, because that's going to be up to date and you're not going to be asking yourself, is the flight code the same as all the modes we designed? Because sometimes that happens if they're not one-to-one. One contender in terms of methodologies for designing your code is an approach called waterfall. And it's called this for the reason you can see here. You start with your requirements, you can analyze those requirements, you come up with your design, code, test, and then you go through operations. It's a very classical approach that's used in a lot of like businesses and so on. But the new standard is really agile. This used to be new, but I'm calling it a standard now because people have been using agile for several decades at this point. And the idea here is that you can go through these planning cycles where you get your group together, you plan what you're going to do, you all execute, and then you come back. And the idea is that this is much faster than waterfall, which requires that you go through your entire operations all at once. And then you get to operations at the end. Agile lets you do iterative testing through the process itself, which is nice. And then there's even people who've tried to kind of put the two together. And with spacecraft development, you kind of do have to put the two together, depending on how lean you want to be. Because oftentimes when we're building our spacecraft, we do start with requirements and mission objectives and so on. So you do have to think about how to break up your requirements into small moments of implementation and so on. I joked about the _new thing before, but that's why it's really important to have a version control system. You want to know what version your software is that you're running, not just for your flat sat and for your testing setup, but you want to know what version's running on orbit. So if something goes wrong, you can run it again on the ground and try to figure out what's happening. There are several options here. There's Git, Mercurial, and SVN, Subversion. Pretty much everybody uses Git now. And I would recommend using Git because you're going to find the most resources for Git. Go over an example Git workflow here. In this simple example, imagine that we're all writing software. You're going to want some main branch that you don't change. You never directly write code on your main branch. Your development branch is where your team is going to put, your development branch is where your team puts all the code that they're currently working on for whatever review is coming up or whatever particular test you're running. And each dot here is a commit. So what do I mean by branches and commits? A branch is a particular state of the software that you can pull down from your server. You can all say like, hey, are you running on the correct branch? Are we running the test in the same branch? It's a very common thing that you would ask if you're trying to do the same test as someone else and verify their code. A commit is when you save your code and you push it up to the server. So if I want someone to test what I just wrote in flight software, I'll say, hey, my branch is this, and I just committed it. You can pull it down and run my branch. This is an example of when you're actually developing. What you will do as a team is you will decide what features you want to add, what software features. You will make a brand new branch, or this is an example workflow. You don't have to follow this exactly. Use what works best for your team, but this is what our team does. What we do is we decide collectively during our sprint planning for our agile approach. We say, like, we want to add the beacon feature. And you can see here, maybe this bottom dot is our beacon feature. And I'm writing code actively and committing to my beacon feature branch. Eventually, I will merge that back into develop and ask everybody on the team to review it and see how it is and like run tests and so on. The nice thing about doing this is it lets the main branch stay stable. You're not breaking anything in your flight software. You always have a stable version of your flight software on main. Your develop branch is somewhat stable. The idea is develop should be stable as well, but sometimes it breaks, and that's fine. And then you have your feature branches that you're merging into develop. And so you can have multiple people working on different things at the same time. At some point, you're going to want to merge develop into your releases, into main. That's called doing a software release. Each time you do this, you should bump your version number. I can't stress that enough. Bump your version number. Don't just keep a main branch that's running. You want to have some idea of what version software you're running, and you want to be able to go back to a previous version and run that in case something broke or something unintended happened. And you're going to do this about once every 2 to 8 months. This is way less frequent than your feature branches you're going to be committing to maybe daily, maybe once every 2 days, depending on how often you're able to work on it. And you're going to typically be doing releases during flight and operations and before and after major reviews. And when you merge, and by merging is when these software branches come back together, that's when you'll do things like unit testing and integration testing and so on. I mentioned these design diagrams. This is kind of what you'd start with if you were working on figuring out what features you want. So you and your team would get together at the beginning of like a build cycle or a development cycle, and you draw out how you think it's going to work. And you may choose one particular component for like each person to work on, or one particular set of this for each person to work on. So you may say, someone's going to work on the Hall effect sensor getting hit detection. And then that will be maybe a series of features. So you may have your Hall effect sensor being a particular feature. You want to add that component to your flight software. And then when you've done that, you can write some software tests that work, and you merge that in. And then you would say, okay, we're going to add hit detection to that. And you'll go through the same process. And if you're using a tool like Doxygen, like I mentioned, you can auto-generate these flow diagrams and so on, these state diagrams with that tool. And you can later, at the end of your build, go back and see how similar it is to what you actually designed. In terms of good coding practices, I do recommend coming up with generic and reusable code. There may be certain math functions or libraries that you end up using throughout your team. It's very important to not be reinventing the wheel the entire time. As far as configuration, you're going to have a particular environment that you're running your code in. And I recommend that you look into how to configure that environment for everybody. Because sometimes when you ask someone to test your code, they'll say, this doesn't work on my machine. Well, you want it to be able to work on everybody's machine. And there's ways you can get around this with things like virtual machines and Dockerized containers. I highly recommend that your team have a development virtual machine that someone on your team maintains. So this is your flight software virtual machine. Everybody writes their code on the flight software virtual machine. And the cool thing about this machine is you can copy and paste the same machine and send it to everybody. Everybody can code on the same machine and run the same tests. When you're designing faults, you have the choice of how nice to make your error messages. And I recommend that you make them very nice and even say what function they come from. All of your error messages should have return codes. You should have some way that you map this to something you understand. So in this example, we have this sort of what I'm calling a bad warning message, which is an error occurred, catastrophic failure. That's not something you want to get from Orbit. What you want is something like, oh, step 3 failed in function do the thing. That makes sense. I understand why that happened. And that's an example log of what that would look like, where you have your debug levels set. So you want to be able to, in your logs, either have all your messages coming through in your logs. That would include things like warning, debug, and error. And this is something you should implement. You should make sure that you have these different log levels. And you always want error messages to come through, always. You might want warning messages to come through sometimes. If stuff's really going bad, you're going to want to have your debug messages. And that's where you can put your messages that are like, I got to this line. So you'll want this stuff in addition to your housekeeping counters and so on. And in general, these sorts of logs are not things you really want to downlink from Orbit. You may have to, but it's not something you want to downlink from Orbit. So this is going to be mostly useful during your integration and testing of your spacecraft. In general, you want to have your nodes be known good states. And you want to have very specific definitions of what telemetry is being gathered in these modes, what the power states are in these modes, and what the fault conditions are in these modes. Because, like I said, an error can occur, and you want to be able to say what that error was so you know how to fix it, or you know even what function it's in. And the return code is supposed to help you identify what line in that function that is, essentially. All right, document as you go. I already said this with Doxygen, but it's really easy to add Doxygen code comments as you're coding. You should really do it. As a matter of fact, as a part of your standard review process, when you're seeing how stable someone's code is when you're merging it in, you can require that people have written a certain amount of Doxygen code. And if they don't, you can say, we're not merging this in yet because we don't know what's happening here. There are plenty of language standards that you can take a look at. For small spacecraft, essentially, any of the common coding standards are good enough. You can look at some of the NASA coding standards. JPL has some as well that are also good. I have some of these other ones linked. Having more lines of code is fine. Your code's not more efficient because it has less lines of code. So I recommend if you've got like having a sort of soft limit on how many characters you can have on one line or something like that. And if you have an equation or something crazy that's happening in one line, just break it up into multiple steps. It's fine. But we are so past the era where we have to worry about that with low Earth orbit. We have plenty of compute. And then if you have issues, you want to track them in whatever system you're using. So you have workflows that actively manage or actively track bugs and features and so on. You'll want to use those as well. I have some linked here. Jira and Bitbucket is a system we use. Jira is just essentially like a Trello board. I don't know if y'all have ever used that, but it's a column of like to do, what's currently being done, and who's doing it, and then what's done. And we'll iterate through that every 2 weeks. And Bitbucket is just our Git server that we use essentially. Those are both pretty good options. There's tons of free options as well. There's really no need for a university team to pay for any of that stuff. Your review structure, you should have at least 2 reviewers whenever you're reviewing code. So I was going through this Git workflow and I was talking about merging before. You want to have 2 people review the code at least. Every review should have a description, or every merge should have in it a description of what you've done, like what you've added and solved, and a description of how to test it. If there's no description of how to test it, that's not a real request. Someone needs to say how to test it. This helps you catch bugs really early. And another thing that should be involved here in the review is automatic testing. So if you're pushing to something like Bitbucket, for example, you're putting your code and you're storing it on something like Bitbucket, you can have it set up so that way when someone commits to the code and pushes or attempts to merge to develop, you automatically run through a series of tests. And this gets me into unit testing. Unit testing is essentially the smallest level of testing that you're going to do. And it's done continuously as you write your flight software. So if I make the function do the thing, there should be a unit test somewhere else in our testing code. Your testing code is separate from your flight software. But somewhere in your testing code that tests the inputs to do the thing and tests the outputs to do the thing. Even pass in some bad inputs. You want to make sure that your system can handle bad inputs and gives you a legible response when you're trying to read the bad outputs from that. Some tools that do this are Jenkins, Travis, Bamboo, GitLab, CI, blah, blah, blah. We use Bamboo. Again, doesn't matter what you use. There is a tool called Gtest that Google manages for free that you can use. You can just download Gtest. And the way that this basically works in the flight software is if you wrote the function do the thing, if we're talking like C or C++ here, do the thing has a header that you can include in the Gtest suite, and then you can have access to all the functions of the code you wrote. And that's where you'll write your test code. Develop simulators and emulators to support your code. So if you know that you're going to get a certain type of packet into do the thing or into your beacon software, something like that, have examples of that packet that you pipe into your test code. The other thing I should mention is that most of these tools can generate reports. So you can see that you have 100% of your tests running, or you can see that you have 20% of your tests passing. I mean, those are really useful if you're trying to get an overview of the stability of your system. Integration testing is a layer above unit testing. So unit testing is by the function level. Integration testing is going to be the component level. So I was talking about your beacons flight software, for example. You may have a particular packet structure that goes into that. Integration test will try to run your beacon for, let's say, 10 minutes. So it's also longer than your unit test, which should run pretty quickly, by sending that packet over and over again. And you may try to inject some bad data into that packet too in your integration test. This helps you build up to your day in the life testing. As you're slowly adding these tests in your flight software, you get to a point where it just makes sense to do day in the life testing next. And that's nice. It's incremental. The other thing about integration testing is that this is when it becomes beneficial to do hardware in the loop testing. This is the first stage of your testing. The unit testing, because at the function level, doesn't really matter that you run it on the actual hardware. When you get integration testing, in theory, you can make your integration testing system such that you can plug two components together and then try to run your integration test between the two components. So instead of having, let's say for the beacon example again, you want to run this beacon example for 10 minutes, instead of having like a CSV or a long text file with all your packets in it that you want to send once a second, you can actually try to plug in your component and see if that works. The way you're probably going to do it functionally is just record what that component does so you can rerun the same test every time. That's also very important. But this becomes the first stage when running on actual hardware is useful. So test coverage, I mentioned that reports can be generated. Those reports are what you're looking at when you're trying to ask the question, do we have test coverage? In general, you should have more test code than your flight code. You can see how this blows up. You want to test your do the thing function with not just good inputs, but bad inputs, right? You can already see how this can grow quite large. And you're doing that for every function you're writing, essentially, every serious function. There may be some that you choose not to, but in general, you should have a one-to-one correspondence with like a unit test in the new functions you're writing. And that's going to give you 100% coverage, essentially. That's what that means when we talk about testing coverage in software here. Don't cut corners with any of this stuff. So when I'm talking about packet types with do the thing, inputs to do the thing, make sure you're using the actual input that's going to go into it in at least one of the tests, in addition to a bad input. Don't say, we know this is about 5 digits. Let's just send 5 digits to it. I'm sure that'll be fine. This will always come back to bite you because you're building on top of this thing. You're building layers and layers on top of this thing. Even though tests may seem redundant at a higher level, because you've already unit tested it, you should do it at a higher level because, again, you're building layers on top of this thing. And you may have components that are talking to each other before that inadvertently affect the other tests you're running. Another way to think about this is some people like view this as kind of like a slog, like, oh, we're having to write so much test code, this isn't fun. That's going to help you not have a problem later. That would also have you writing a lot of test code and you wouldn't even know where it was. In theory with this, now when a problem happens when you add a new component, you can narrow into the exact unit test that failed and the exact integration test that failed, and you can know how to fix it as you're building under your flight software. And then lastly, these unit tests are also nice because it's essentially a tutorial about how to use your flight software. As you're writing your unit tests and your integration tests, you could have a new member come onto the team. They're like, I don't understand what's going on in this component. And you can say, well, in this integration test, I sent the component these inputs, I got these outputs that I expected, and it went wrong in these ways, in the ways that I expected. I recommend you make your unit testing code very verbose and your integration testing code very verbose because there's no reason to cut back on the amount of comments in that or the amount of test cases in that because it's not flying. It's just for you. It's just for your team to know what's actually happening in your flight software. This is not something I expected when we began doing this with our team, but it's been very helpful for when we onboard new members and so on. Here's an example of what we do. You can see that we have unit tests. We use the Google test, G-test to run these tests. It's not important what these circles are, other than you should know they are applications running an total electron content experiment and running a cross communications experiment. And when we're doing unit testing, we're testing just those components, just little functions in those components. When we're doing integration testing, we're gradually testing different ways that those components talk to each other on the software bus. And when we do swarm integration testing, this is less important if you're only doing one spacecraft. We use Docker to simulate the spacecraft and simulate them talking over a network. We also utilize the testing framework for scenario testing. So I said that this builds up to a day in the life style testing thing. If you're doing it right, it becomes really obvious at some point when you have your integration testing that, oh, if you just attached actual data to the main input for your whole spacecraft system, you could in theory try to run it for like 2 days and you can get some output from that. That's all that this second column is showing. And then there's different environments that you can run this on at different points in time as it becomes useful for you. The containerized testing environment is pretty much going to be useful from day one. You're going to want to come up with a virtual machine or a containerized testing environment. Those could be more or less used interchangeably here. Anytime you see container, you can put virtual machine. And then you can run it on the processor in the loop once you have your software components talking to one another. And then you can move to a hardware in the loop with even more hardware. Maintenance is just something I want to mention briefly, that you'll get to a point with certain components where you're not developing them actively anymore. And that's when having bug tickets in the background and having all these unit tests and integration tests is really nice, because you can go back and you say, I remember we had this problem one time and I wrote a unit test to fix this problem. In the unit test or the integration test, you're going to essentially in the code replicate the problem and then show that it doesn't happen anymore. And that is almost in itself a form of documentation. So that's what I'm trying to get across here. All right, we'll go over the data budget briefly. So when you're coming up with your data budget, you're trying to understand what data you're generating on board. You're up there to do something, and you need to understand what you're doing. So you want to understand your data sources. You want to understand your data rates. So how often are you generating this data? And you want to determine where you're storing it. And you got to think of your margins of error and so on. Typically, your data budget is dictated by communications with your ground system. So if you don't have a ubiquitous ground system, or the ability to communicate all the time with your ground system, that's going to affect your data budget. So you're going to need essentially more storage, depending on what you're doing. And the third bullet here is bits per contact is your link time times your link rate. That's really what you want to think about there. And in terms of data volume, just the key thing to take away is this diagram over here on the right, is that you have some input rate and you're filling your memory, and there's some output rate, and then there's a buffer in addition to your fullness. And so your expectations as to how quickly this is going to fill are going to drive tons of requirements related to your CDH. And also, this is essentially what your data budget's trying to capture, are the variables in the situation. And then once you have the variables of the situation, you can play with your concept of operations to understand how you can do this, or maybe you need to increase your memory. When we're thinking about memory management, I always have to think about, what if we don't get a communication? Is this going to overflow? And then if that overflows, you have to think about, how are you managing the overflow? What are you going to do? Are you going to stop taking data? Are you going to overwrite the oldest stuff? Are you going to overwrite the newest stuff? When you do get communication again, what do you want first? Do you want the newest stuff? Do you want the oldest stuff? Did you stop taking data altogether? These are all things you need to consider when you're designing your system. I would say in general, for housekeeping and telemetry, if you're in a nominal mode, if you weren't in a safe mode or an emergency is not happening, you want the newest information. Here's an example of overhead, right? I think people, when they're going through the data budget, just often forget that there's overhead to every packet that's sent. This is just an example of what that can look like, where you want to sum up all the bits in your overhead and make sure you add this to each packet that's sent over time. Margin is important. Talked about kind of the motivation behind margin. I'm not going to go into this in detail, but this is how you calculate it. And there are different points where you want to think about how much you have. Here's an example. And again, this is mostly for your own viewing later, but you can have an example system here. This is what a sample data budget looks like. This is kind of where I really wanted to get to. You have some time required, a link time available that you can get based on the number of contacts you have and how many days and so on. And you calculate your data budget by taking the number of bytes you expect to generate with your particular component. You make sure you add your overhead. You have some frequency at which you're getting this data, and then a duration over which that frequency is applied. And then there's some of your total times the overhead. That's essentially, that's it. That's as simple as data budget is. Now, what this is not showing is that your payload may be generating different types of data. I don't recommend having it be this simple. This is just this simple for the case of just kind of fitting it on the slide. So you may have something like, I don't know, maybe your payload is generating health telemetry, housekeeping telemetry, and other things as well that you want to break out into other sections. Anything that's being sent over the bus and stored should be in the data budget. Anything that is stored is in the data budget. So we'll get into trade spaces, and this is the last section, trade spaces for this and flight software. So as you're selecting your components, there's 4 stages that you're going to go through. This is a workflow that we use internally. So this is what I would call guidelines. This is not a standard. You don't have to use exactly this, but I'm going to walk through kind of how we go through selecting components for our flight software systems. We go through this trade study over here. So the first phase is to find information about your requirements and generate your requirements for your CDH system. This is different than your mission requirements, but your mission requirements are probably going to be in here. You may not have a full set of your mission requirements in here. So the first thing to do is this is all in a document. You're documenting this. You want to be able to go back and reference this later. You're going to write about the purpose of what you're doing and why you're doing this particular thing. And then you want to talk about any expected results that you, in terms of like outcomes, not necessarily what exact system you're going to get. You want to talk about what's going to happen when you complete this trade study. What are you going to do with it? And then is there an option to not use this trade study at all? Then you're going to begin to develop requirements. So you're going to have these things like go and no-go requirements. You're going to have objective requirements and you're going to have subjective requirements. So the go and no-go is, I'm not a controls person, so I'm kind of poorly using an ADCS as an example here. In this case, it's the ADCS shall have a mass no more than 200 grams. That's a binary statement. That's going to be in your go, no-go requirements if it's a binary statement. And then for objective requirements, you're either trying to minimize or maximize them. And if you really want to get fancy, you could use a different function, but keep it simple, just minimize and maximize these objective requirements. In this case, like a lot of things, we want to have minimum mass, and let's say we want to maximize mounting points. I don't know if that's a thing that these controls people do, but that's what I put as an example. And then for subjective requirements, you'll say something like, we want the attachment points to be in easily defined areas and places that are nice. So that's obviously subjective. I'll get into how we work with that. Our team was building a test track for 100 flight computers, and I'm using that as an example here. Again, this is kind of for you to look at later if you want to go through this process yourself, but the key thing to notice here is that we have a list of objective requirements that are go and no-go, right? So we've got a few things there that have to be on the system. For example, one of the things is at Ames, we use the core flight software system. That's a NASA system for flight software. And so we knew we had to use that one because we're trying to rerun certain components and we wanted to be able to interface everything over gigabit Ethernet. So as an example. And then for objective measurements, well, we wanted to minimize cost, of course. And then we wanted to do all these other things. And then you can see a list of subjective requirements. One of them is ease of virtualization. Right? We wanted to be able to virtualize these processors in VMs or Docker containers and things like that. And it's subjective about how easily our group finds that, right? And then we have a good balance of processor selections there, just as another example of we wanted to find the good balance of these things. What does our team deem a good balance? It's something we would talk about. This is what it looks like when you go to phase 2. Essentially what you're doing is you're making a bunch of matrices for the rest of this trade space. In this case, I think we had over 70 total trades. So I'm showing you a few of the options. But here we have a list of processors, whether they met our go and no-go. And then we've got some of our go and no-go statements there. You really want to put all the possible information you can in this, because ideally, if something changes and maybe one of your go no-goes is no longer a go no-go, or you have a requirement modified or loosened or tightened or something, you want to be able to change that and then see the outcome of your trade study with that being changed. So it's important to go ahead and fill out all this stuff, though you might still have some unknowns. And you can make this as complex as you want, really. It could be simpler or more complicated than this. The phase 3 is when you begin ranking everything. What we do here is we have, in this case, we can see our objective and our subjective measurements. This is after we've gone through the go, no go phase. So we decide all stuff that we could use. Essentially what we're doing is we rank the objective measurements. So there's going to be something we can get from an ICD or a measurement of wattage or RAM or the total cost of the solution. That's objective. So we can write that down and then we can multiply that by some weight and then sum it all up. And then we normalize it at the end. And then we have the subjective measurements too. I think it's nice to only use 3 variables there when you're doing your subjective rankings. I think it's important to include subjective rankings, but I think it's important to not use too wide of a scale. Like 0 to 10 is way too much fidelity for that. I think just having a 0, 1, or 2 is fine for that, with 2 being the best and 0 being the worst, and 1 just being average. And this phase of your trade study just consists of reading a bunch of spec sheets and getting quotes from suppliers, things like that. And then at some point, when you sum up all these values, you'll get your scores. So we use a 70% objective, 30% subjective measurement. So in that case, we're weighing towards the objective, obviously, but it's up to you to decide how much you want to use. You could just use objective if you wanted. And the point here is after you've done this trade study, your team shouldn't have to argue about what is the best solution anymore. Everybody should be involved in the trade study. Everybody should be involved ranking it. As a matter of fact, when I did the subjective measurements, I didn't mention this before, but we got our whole team to rank the subjective measurements, and then we averaged the rankings that we all did. So the team's opinions are already baked into this score. And then in theory, based on how much you consider to be a good threshold, any of the top solutions are good. You can pick any of these arbitrarily, and you'll have the ability to defend your solution in theory. And really what you want to do at this point is develop a path forward. The following two stages are optional. You can choose to do a risk calculation, a risk assessment with your solutions. So like I said, the top 10 are all good. Maybe one of the top 10 included a series of boards that happen to have not the best radiation tolerance. And so if we wanted to add a risk assessment, we could then rank the top best solutions by risk profile or something. That's something you can do if you want to do it at this stage. We did not do that for this because we're not flying this solution. We're just running it on the ground. That's what our final component selection looks like. And I think it's really important to come up with a pitch deck, or you could call it closeout documentation. You should be able to go to anybody who's asking questions about this, your stakeholders or customers who are like, why did you do this? And you can give them a short summary about why you chose this solution, why it's good, and so on. That can also be for you and other team members if they're curious. And of course, you can always go back into the rest of the trade study to tease out the details. With that, that's the end of the talk. So thank you all for listening.